So today we're gonna be introducing a separation technique known as distillation. It's an efficient purification technique which is used extensively in different industries to extract compounds from raw materials. Some of the most common applications of distillation are the processing of liquor, the processing of crude oil to obtain usable fossil fuels, and the extraction of medicinal compounds from herbs. So, in today's discussion, we will include the distillation of ethanol in our experiment, which has the properties that we want to take note of. Its boiling point is at 78.5 degrees Celsius, and we should take note that it's in its structure. It has a hydroxyl group. We can kind of predict already that when mixed with water, both compounds will have strong intermolecular interactions due to the electronegativity of the oxygen atom and the hydrogen substituents. Let's keep this in mind for when we attempt to separate them by distillation. And you can kind of see here that you can see the attraction between the hydrogen proton and the oxygen ion. This is what a standard simple distillation apparatus looks like. We're going to be having our heating source, our heating mantle right here, and also our round bottom flask, which will contain our unknown sample and the compound that needs to be extracted. We also need to place a thermometer at the top of the apparatus, which will need to put it at a critical point that will measure the vapors, the temperature of the vapors that are going to evaporate when we reach a high enough temperature. We also need a condenser that's gonna be cooling down our distillate from its vapor phase into its liquid phase, and we take note that the water flow through the condenser is going to be in a counterclockwise direction. We also need a receiver. That's the volume of it will depend on the amount that's to be extracted. In this case, we're only going to be extracting about 14 milliliters of the distillate, so 10 milliliter graduated cylinder is probably enough for this experiment. Some things to take note of the experiment itself is that we need to secure the apparatus in most of the areas so that it won't tip over. We also need to make sure that when we connect the water hoses, they flow in the correct direction, and make sure that the hoses don't accidentally are placed over the counter, which will then overflow the entire area. So we are careful with those items right there. We will also be performing a second type of distillation called fractional distillation. Essentially, we have the same apparatus as before with an additional fractional column shown here. The column is packed with Rayshag rings, which are cylindrical rings that improve the efficiency of obtaining a pure ethanol. And we will discuss how they perform that mechanism in a later slide. So what's happening during distillation? Well, the mechanisms are easy to follow. Initially, the solution is continuously heated, and the mixture will be evaporated and will flow through the in an upward direction into the condenser, which will then the vapors will experience a cooling effect from the water flow that's traveling in the opposite direction. We record the temperature of the vapor just before it cools off at about half milliliter intervals, and by cooling the vapor, it returns into its liquid phase and eventually collected in the receiver. The apparatus shown is our simple distillation, and in order to obtain a pure substance, we need to repeat it various times. The first distillate would probably have a pure composition of ethanol of 50%. Doing it again would probably give us 70%, and again would probably give us 90%. Why the inefficiency? Well, it could be from we can see our phase diagram here for just about any liquid. In this case, let's say that it was a water. We see that the water exists in two different phases. It could be in the solid and the gas phase and the liquid phase. When it's in its liquid phase, it's going to be also a portion of it is going to be into vapors, which will also be collected along with the ethanol that we're trying to extract. To obtain a pure substance, like I said, we're forced to repeat the procedure a few more times to increase the purity of our compound, in this case ethanol. So if we were to heat up water by itself, we would see a temperature increase constantly until it reaches to 100 degrees Celsius. At 100 degrees, we would see a momentary stop in temperature increase until all the water would vaporize, and only then would we see a higher increase with continuous heating. The same behavior would be for ethanol, but at a much lower temperature. In this case, it would be 78.5 degrees. However, when we mix our two compounds together, we collect our distillate at lower temperatures, which is lower. Half of it we would collect it at under 79 degrees Celsius. Only afterwards did we see an increase in our temperature relative to the amount of distillate that we received. However, when we repeated the experiment using fractional distillation, our boiling point remained relatively constant throughout the entire distillation. Additionally, the boiling point remained below the known values of both ethanol and water, and we can partly attribute to the constant boiling point to the fact that water vapors are recondensed when they come into contact with the Rayshad rings in the fractional column as they attempt to travel upward. Only the more volatile substance is physically able to flow through the column, where we then record its temperature and collect it in the apparatus receiver. We obtain a much purer substance by this technique, which is slower compared to simple distillation. So when using our fractional distillation apparatus, there is a mechanism that is happening, which is a repeated distillation that's happening inside the fractional column. What we can see here is that when we're at this point right here, we have our liquid composition, and it evaporates into a vapor composition. And what happens here is that we recondense the liquid, and when we recondense it, we again turn it into a vapor composition. And this process repeats constantly, and it substitutes a needed repeated distillation using simple distillation, which would be more time consuming and less efficient. We notice here that if we were to be at the original point here, our ethanol composition would be maybe about 20%, whereas it travels into the vapor composition, it increases maybe up to 30%. Since the mechanism is happening in the fractional column again and again every time that the water vapors condense in the Rayshad rings, we see again that when we go down back to the liquid phase, we again travel horizontally into the vapor phase, which by now should be at 50%, which would be at 50% ethanol. And as the process repeats again, the ethanol would increase in 70%, and then again into the vapor phase would be 90%. So this is what's going on in a positive azeotropic mixture. This is a more efficient way of doing the experiment. We reach a point, for ethanol, we reach a point up to 95.6%, which is the most possible, the purest substance we can get using this fractional distillation. So why the lower boiling point with this specific mixture? Our ethanol mixture is known as a positive isotrope. Isotopes are labeled as positive or negative, referring to their lower or higher boiling points, respectively, depending on if the compounds exhibit a higher boiling point when compared to their constituents, or a lower boiling point. This could be attributed to the strong intermolecular attractions between the hydroxide ion in the ethanol and the positive dipole of the water molecules. Both hydrogen bonding, which is a strong type of bonding, and a dipole intermolecular attraction contribute to their deviating boiling points. Additionally, both solvents are polar in nature, so we can expect them to mix well and have some degree of attraction. In our experiment, we obtained an unknown, numbered 15, which, when undergoing distillation, produced 14 milliliters of pure ethanol. Since our volume began with 20 milliliters of water and ethanol, we calculated that our original mixture was 70% ethanol and 30% water. This was evident in the data when our recorded temperature spiked after the 14th drop was collected, which indicated that our isotropic mixture did not contain enough ethanol to keep the boiling point low, which would have been deviating from the normal boiling points. So I'd like to thank you for watching this presentation, and I hope this was informative enough to understand the basics of distillation.